This video deals with horizontal shrinking. So let us again look at the general formula for the cos function, which is written here in blue. And if I look at the a in front the coefficient here of the coefficient of cos theta, the a, I see in this case I just have a 1. So there was no vertical stretching, and I can immediately say the amplitude is still 1. But if I now go to my next unknown here, the b value, that coincides with the 2 here. So that means that this new graph, cos of 2 theta, goes faster, twice as fast as the original function through a period. So, and we can see here, if I look at this part here, from there to there, we already have our bucket, and then again, or our cup again there. So it went through twice in the same time that the regular cos graph completed that period. So in this case, our period will be 360 degrees divided by 2, because it is a shorter period, which just gives us 180 degrees. If we look at the roots, then we see that we have more roots now. So we have intercepts now at J, at M, at N, at P, at R, at T, at U, whereas we have fewer intercepts for cos of theta. So let us look at cos of 2 theta equal to 0. That's the same as when we solve cos of x equal to 0. Now, the roots for cos x equal to 0, we will get x equal to 2k plus 1 times 90 degrees as we had before. So we will, in this case, let my x equal to 2 theta. So 2 theta is then 2k plus 1 times 90 degrees, where k is an element of z. So that means that we will have 2k plus 1, 2k plus 1, and then divide by 2, so the theta is then like that, which gives us 2k plus 1 times 45 degrees, where k is an element of z. And you will notice here, our first one there is at 45 degrees, and then the next one is at 45 plus 90 degrees, which gives us 135. The next one, if I add 180 degrees, I will get there. Or if I put k equal to 0, the first one will be at 45. If I put k equal to 1, I'll get 3 times 45, which gives me 135, etc. So please check your formula. So you can also write it simpler if it's easier for you. So in this case, we put the x equal to 2 theta. We use the old graph. We use the cos x, the basic one, to help us find the solutions. So if we know that solutions, then we just solve from there onwards, we solve it. Okay. We look at the minima and maxima, the three extremes. They are exactly the same as before. We still have a minus 1 and a plus 1, but they just occur frequently. So we have now minima, for instance, at k, at o, at s, and we have maxima at c and g C, Q, and G, etc. And we can write down again a formula for our minima, and they will occur. It's not the minima. The minima are still minus 1. The minima are still minus 1, but they occur at, for instance, minus 90 degrees plus K times 180 degrees. Previously we had 360 degrees, so it's shorter period now. And the maxima occurs at theta equal to, if we look at the first maxima, that's at 0 degrees plus K times 180 degrees, where K is an element of Z. On this page you will find the neat summary, and what you should notice again is that this 2 here coincide with this 2 here, but we previously we have used that for the amplitude. Now the period is influenced by the B value of the general formula for a cos graph. So the amplitude is the amplitude is the same, but the period is half the size because we multiply the theta with 2 and not the cos with 2. So please look through these exercises or the summary and make sure that you understand where each and every formula comes from. So, and also that you know how to solve cos of 2 theta algebraically.